All right, thanks for coming out. Wow, big crowd to talk about one of the most grubbiest things that we do in Hadoop, but one of the most common things, data preparation, or data cleansing, or data munging, as I like to call it. I always like that word. It's more, I actually like data grubbing, for reasons that will become obvious later on. So, my name is Casey Stella. I work for Hortonworks. I am an engineer and data scientist on the Metron team, on the Apache Metron team. Before that, I was in the consulting organization. I was a data science consultant for like 3 years in Hortonworks. So I've been around, I've seen a lot of data. I've seen a lot of data science as well. And before that, I actually worked at a startup doing medical informatics, which also involved a lot of data science and involved an exceptional amount of data cleansing. So one of the, my background is in math with Texas A&M. So there's not going to be actual math involved in this. I don't want to scare anybody away. So, but there's going to be perhaps some mathematical terms that I'll describe. So before I do this, I always like to do this in talks. So how many of you are working data scientists today? Like how many of you would you call yourself a data scientist? All right, how many of you are managing data scientists? All right, what are the rest of you guys doing here? I'm just kidding. I'm just kidding. So DJ Patel said 80% of any work in a data project is cleaning the data, and I think he's actually underestimating. I don't think he's seen some of the nasty data I've seen in enterprises or in medical, certainly. But the fact is, it's a truism that garbage in equals garbage out. Garbage in implies garbage out, right? So if you put garbage in, you're not going to be able to trust your insights coming out. It's very important. And a lot of people I see, I go around to talks, I go around to conferences a lot, and I see vendors proposing some of the solutions to this, right? But they're never quite complete, in my view, from what I've seen and what I've had to actually implement. So there's really, data cleansing implies data understanding, right? You really have to get to the point. The act of cleansing your data leads you to understand your data better. If you're not actually doing the cleansing part, you don't have a full understanding of your data. And that's a bitter pill to swallow for a lot of organizations and a lot of teams. And we'll get to the implications on how you construct data science teams, in my opinion, later on in the talk. There's really two ways to understand your data. There's a syntactic understanding and a semantic understanding. We'll talk a little bit more about those. But if you really hope to get anything out of it, you have to have a solid understanding of both, a solid grasp on both of those dimensions. So when I talk about syntactic understanding, actually, I'm going to go back. Let's talk broadly about what I mean here. So syntactic understanding in general is, what does the data look like from a kind of a cursory level? And most of the things that you see, like the counts and the word counts and the SQL queries that you see around the data cleansing and the data understanding are syntactic understanding. It's, what does this data look like from a kind of a cursory level, right? I have a SQL database, I have a Hive database, right? Or I have a CSV file. I have columns in that CSV file. How many are null? That kind of stuff, right? The semantic understanding is more, what does it mean, right? We'll get into that a little bit more. So the first dimension, or the first part of a syntactic understanding, in my opinion, is understanding the true type of the data. So I don't know how many times, I don't think I've ever been in an organization that didn't have string columns in everything. Right? If I go to a Hive table, I'm expecting a string column. Like I'm absolutely, if I get an int, I am shocked. And I know I'm probably losing data if I do, right? So a true type is a label applied to data points such that the data points are mutually comparable. What does that mean? It means I could have a column where I mix numbers and words together. So what that means is that column has multiple data that has data from multiple true types, right? So that they're mutually comparable. So, and the schema type does not equal the true type at all, right? So One of the best examples of this is lab data. So I come from a medical background, so I'm gonna kind of use those as examples. So lab results. When you look at lab results, you'll see anything from, so you go get your blood work, right? It comes back, and the actual database, how it looks in the database is lab test, and then value, and then unit, right? The value can be anything from a number, like your cholesterol level or your blood pressure level, to a color, like the color of your urine, right? Those are not mutually comparable things. I cannot compare my blood pressure with the color of my urine. They're both types. I'm not saying that the scheme is wrong, but I'm saying that you have to dig deeper to even understand syntactically to pick those apart. The data scientist has to dig deeper and to separate those true types, right? But the first way, before you can separate them, you have to understand them, right? What's actually in the data. Okay. The next part of syntactic understanding is understanding density. So what data density is, it's an indication of how clumpy the data is. It's highly technical, I promise you. But if you really think about it, like this generalizes. So for numeric fields, distributions and statistical characteristics are how we encode that. We've had generations of really smart people thinking about how to think about numeric density, right? These aggregation statistics, that tell us something, maybe not the whole picture, but some of the picture, right? For non-numeric data, what you generally find are people doing counts, right? Counts, distinct counts. But what I don't often see, and what I find myself always doing, so this talk was born out of all the crap that I do when I get a data set. If a client gives me a data set, this is the stuff that I do first. These are the things that I think about. That's why it's called field guide on the title, right? So for non-numeric data, you look at counts, you look at distinct counts, but what I often find myself doing is actually wanting to get to some sort of canonical representation. So I'll give you an example. I'll tell you a story. When I was at Explorus, I'll tell you two stories, in fact. First story. When I was at Explorus, we were doing medical informatics, and we wanted to do some identity management, right? We were getting data from different hospital systems in. You could go to hospital A, and you can go to hospital B. We wanted to be able to join your records together. You would think this would be an easy thing to do. You would think it would be an easy thing to do even within the same hospital system, like the Cleveland Clinic. It is, in fact, not an easy thing to do. So you say, well, you have social security numbers. Surely you have social security numbers, so that will be an easy way to join this data together. You would, in fact, be wrong. People cannot type numbers. That is a problem. We're very bad at typing numbers as humans. Very, very bad at typing numbers. So what you end up having is people saying, I don't know the social security number, so I'm going to put all zeros. Or I'm going to put 1, 2, 3, 4, 5, 6, 7, 8, 9. Or I'm going to fat finger 1. Or I'm going to put an O instead of a 0. So you get all kinds of different formats. I'm going to have some with dashes and some without dashes. Remember when I was talking about string columns? That's what I'm talking about. Some with dashes, some without dashes. So what you do is you look and you get counts not based on the number of, not based on the number of social security numbers, though that is informative, but a lot of data. But what you do is you get a count based on the string replacement of the number with the letter D. Then you get all the different forms of social security numbers that you have. The same thing works for dates very well, actually. The same thing works for goods, I found, that people will often pull over and fat finger. Anything that involves the mixture of numbers and letters, people will make mistakes. And this is a good way to do that. There are other kinds of canonical representations, right, where you just have things like word length, just the textual length. You expect everything to be, 5 characters, but how many are actually 7 characters? How many have a space in them, right? 2 lowercase spaces. I know this is the data science section, and he's talking about 2 lower, but this is the stuff that you do as a data scientist, I promise you, because I have to do it a lot, and it's painful. But doing the counts on the canonical representation of the data gives you a really good idea of what constitutes the data. It gives you an impression of what's there and what's not there, and what are the obvious mistakes. Because the point of the data munging is to either remove the mistakes by removing the data or correct the mistakes, right? Hopefully correct the mistakes. Actually, I promised you a second one. Second story. So I had a colleague at Explorus. He spent 6 weeks normalizing height data. 6 weeks, just on height. That's one measurement. It's a very common measurement. People use centimeters, people used meters, people used inches, people used nothing. Sometimes you just couldn't tell what they were. Sometimes you had to use the number to figure out what they actually meant. Sometimes you couldn't use the number because there's that nice little overlap where it could be a centimeter, it could be a centimeter, or it could be a foot type of measurement, or inch type of measurement. You don't really know. It was one of the most complicated parts of that software stack was figuring out what the actual height meant. It's very difficult. And so I thought, we have to be the only people who has this problem. So I went and one of my first clients at Hortonworks came in and said, we have a real problem with really fat midgets. And I said, what do you mean? He said, people can't type height right, and people can't type weight height right either. I said, you know, you're right. It's all over the place. Absolutely all over the place. So this talk is not about fixing that. This talk is about understanding that you have a problem. Because the first way to fix a problem is to understand you have a problem. It's okay, this is a safe place. So the idea is that they give you some idea about how the data is shaped at a glance, right? Data density is an assumption underlying any conclusions drawn from your data. Now, I know you're gonna see this, from a lot of data scientists are gonna talk about this. I even have a book on Amazon about data munging. Download it if you want, but you're gonna see this. The next part is something I haven't heard people talk about, and something that I think is absolutely imperative that I suspect no one is doing. And after I finish this slide, I'm gonna ask the question to raise your hand if you're doing this to your data, for your data. Not to your data, for your data. Because it's unhappy without this, I promise you. Density over time. So we already know how data clumps, right? But what we really want to know is how data clumps over time, right? How does it change over time? We want to know the first derivative. Promise you a little bit of math. We want to know the first derivative of data density. So what it shows you, and what do I mean by that? What do I mean by first derivative of data density? I mean by looking at how does it trend? How does the density trend? Am I getting data of this? If I get 17 data points of this format today, and I've gotten 17 or around 17 for the last month, and all of a sudden I get 300, what happened? So what it highlights is problems in your data pipeline. Because data scientists aren't doing their job if they're not pointing back subtle bugs to the data transformation engineers. Right? That's the point of the data scientist. That's the other dimension to our job, is to be part of that feedback loop. What it also is, it tells you whether your assumptions of your analysis are violated. So I have built so many dashboards for like CEOs and things like that. Directors, people who want to know what's the quality of my data. I want to get the vital statistics in my data. It's mostly because I've worked for a lot of doctors. Doctors are really crazy about getting vital statistics of things. And they want pretty dashboards. They want to understand, like, am I okay? Because they'll log in at like midnight and they'll say, is my data okay? Because if my data is okay, then I'm okay and I can go to sleep. But if it's not, then I'm getting a call. And that's unpleasant. Because I don't want to get called at midnight over some dashboard issue. But if you don't have a handle on how the density is changing over time, you're missing important assumptions on your analysis. So I'll give you an example. Back to the same startup that we were talking about with height and weight. We were having problems where we were making a lot of assumptions about drug types. So one of the things that we did aggressively was look at this density calculations over time. And Hadoop is fantastic for this. So what we would do is every night we would gather how many of each drug, how many patients have been prescribed this drug every night, and we would push it to TSDB. Who here has heard of TSDB? I love TSDB. I love time series databases. They're my favorite. They should be a part of every data stack. We push it to TSDB, and then we would do outlier analysis on that to find situations where there were deviations, right? We found that the Cleveland Clinic suddenly stopped using a particular type of drug, and it was a very important drug for diabetes. I said, how in the world is this happening, right? It's all of a sudden dropped. It's just dropped through the roof, or it's just dropped through the floor. Why is this happening? So we called the Cleveland Clinic and said, yeah, you know what, we transitioned policy to move to generics. So it shifted from one bucket to the other, right? This highlights another point. When you do your data density, you want to do data density at multiple levels. Density calculations at the individual drug level, like in this example, but also one step above, where you're generalizing and saying, okay, if I'm taking aspirin, if I'm looking at, I want to look at not just the number of times that aspirin was prescribed, I want to look at the number of times that any analgesic was prescribed, and all the way up the stack, all the way up the ontology, if that makes sense for your data. By telling us that, all of a sudden our dashboards around drug usage may have had assumptions violated. So we needed to talk to the analytics team. Again, data science, giving feedback to up the stream as well as down the stream. But they were very impressed that we suddenly figured this out, like all of a sudden, they're like, hey, we just did this like yesterday. Anyway, so it implies you have to have automation for this. The other nice consequence of this kind of analysis that you should be doing with your data, because your data is unhappy if you don't, care and feeding of your data is very important. If it's unhappy, it's like those Tamagotchi pets, they just die. You don't want that, right? It forces you to become mature as an organization. It forces you into automation, and it forces you into automation that's extremely doable, right? It's not exotic data science. Doing counts, really not that hard, it turns out, with Hadoop. It also implies that you have to have some amount of outlier analysis and alerting. That is also a step on this maturity, a step on the data pipeline maturity, in my opinion. That's where the data science rubber hits the road. I love outlier analysis because it's not super hard, necessarily. It can be very hard, but it's not necessarily super hard to do. But it's very doable, is the other thing, right? Okay, so semantic understanding. Do what I mean, not what I say. I say that to my kids all the time. It turns out I'm not a very good communicator, so I don't know how I'm communicating effectively to computers, because they're even more obtuse than my kids sometimes. So semantic understanding is understanding based on how the data is used rather than how it is stored. Now, what does that mean? Let's pick that apart for a minute. How the data is used. So normally, all the analysis that we've talked about thus far takes into account the context is a single data point. I can do a transformation on a single data point, and I can tell you the canonical representation. I can do a transformation on a single column, and I can tell you the count, right? The distinct count. Semantic understanding goes cross-column. So when we construct schemas, we have to think deeply about how data is organized, what's connected together. Putting a data point with another data point in a row is not a random occurrence. You've meant to do that. You've associated that. We don't consider the power of that association most of the time. Semantic analysis is taking into account how the different data points are connected. Finding equivalences based on semantic understanding can often be context sensitive. So what do I mean by that? So what I mean by that is, what happens when I wanted to look at the drugs in the previous example that I talked about, and I wanted to move up a layer. What if someone mistyped a number on a drug code, right? Because drugs are coded with a particular coding scheme. If they mistyped a number, I should know what they actually meant, because you're probably not going to prescribe an analgesic, or you're probably not going to prescribe this within the context of that row, right? You should be able to know how it's used, or at least have some sort of guess. True semantic understanding is that, being able to guess the actual errors based on what they mean. Because you're not going to always be able to tell when someone fat fingers something, right? You're not going to always be able to tell when a typo happens. But you should be able to get a hint based on how it's used. And it also may come from humans. So the examples that I talked about before, the fact that we were able to do such great analytics in healthcare is because there's been a lot of public money and public effort put at organizing the data types there. There are hierarchies of codes. There's a coding ontology. So we've constructed this out of human effort. But if you don't have that, a lot of times machine learning helps. I've been in that situation too, where we're trying to find the organization. You have a bundle of sticks and you're trying to figure out, does it form a house, right? Stick house, which is a terrible type of house to live in. Don't live in a stick house. And let me put your fears aside. This is not true AI. This is not particularly hard to do necessarily. It's just using the right pieces. It's picking them apart and putting them together. Right. Okay, so I'll show you the demo. It's screenshots right now. So what I've done is I put together a utility that I use whenever someone gives me a data set. And what it does is it picks apart the syntactic. It does a syntactic analysis. And it does some guesses at some obvious semantic analyses, right? And one of the things you'll note about this is that it is not a sexy website at all. It does not have, it's not very interactive in the sense that, you know, it's not spinning up a server that you're connecting to or anything like that. And the reason why is because when I get in client sides, most of the time they don't let me move their data from the edge node. So I needed something that I could connect, pull down the insights, and use right there. Okay, so it's a utility. It's pretty easy. There's some options. You can specify an input source. You can specify a mode. Right now, it's SQL or CSV. You can also do SQL statements inside of the CSV. Underneath the hood, this is using Spark. It's using a combination of just normal Spark along with MLlib. Do various things. So in order to do the numeric sampling, or in order to do the numeric distributions, you give it a sample size. You can do for both numeric as well as non-numeric data. You can specify the percentiles that you're interested in for the distributions. And you can look at for the semantic analysis, what we're doing is we're taking the row and we're abusing word2vec. How many people have heard of word2vec? Word2vec is, so it's good, some people have heard of word2vec. Word2vec is a vectorization model that MLlib supports. It's generally used for natural language processing, but I have made a bit of a career out of abusing it. So what I generally do for these kind of things, and I found this works very well, is you treat the row, each element in the row, as like a word. And sometimes, though it's not done in here, though I've done this in the past when this utility was written in Pig, what you'll do is you'll take for numeric data, you'll replace the actual value with the percentile, right? So you bin it, right? Obvious binning there. And then you run word2vec, you get a vectorization model. And then you find what are the most likely synonyms for a given column. And you'll see what it shows. So what I did is I ran this on some medical data. There was a Practice Fusion data set around. It's an electronic medical record system. I like using medical records because everyone has some sort of context around medical records. You've all been to the doctor if you've been born. I guess it's possible, but you didn't go to the hospital to be born. But most people have been to the doctor. They've interacted with the healthcare system to a certain extent. So what it does is it's a curses interface. And one of the main things that I look at, the first thing I look at is what's the percentage of columns of data that's missing. Because 90% of the time, I get data that's empty, completely empty. They'll say, I'll get you an export from this system, no problem, here you go. And it's all nulls. So I kind of want to figure out what's going on there first. So for each column, you can kind of drill in and see. So summary for the HL7 column. So at the top, you can see the simple count statistics. The number of valid strings in this data set was 29,000, very small. But there was only 348 distinct strings for this particular data set. And so some examples here based on the number of instances. This is the canonicalized representation. So if there were digits in here, so what the canonicalized representation for strings, the default implementation is just to toString and trim it and replace numbers with the squiggly D, right? So lots of bilirubin. So lots of people doing tests about jaundice. So the point of this, at the end of this, I have questions that I can go ask people. And I understand the data a little bit better than me just running a bunch of random Hive queries. Now we get to past the syntactic correctness, past the syntactic statistics, we get to the more semantic statistics. So we want to see how are these tests used together. So for this particular text, it says that there's a strong connection between albumin serum and bilirubin. Well, it turns out that those are two sides of the same coin when you're testing for liver, for jaundice. There's a covalent connection between bilirubin and albumin, right? So it's picking up that. It's not a syntactic, it's not an equivalence, but it's a connection that you should look at, right? The other thing that it finds is, by the way, that iron saturation and the prostate-specific AG, if you look that up, I actually Googled that later, there are research papers connecting people with prostate cancer and iron levels, just by the way. So it finds that connection of the data just kind of at random. But the more important thing is at the bottom there, I would say. The EGFR and EGFR African American. If I'm trying to normalize the data and only look at EGFRs, I know that I have to collapse those two values together. I would not know that if I hadn't looked at this, right? And there's more down there that you can't see. Most of them are just connections and how the various lab tests are used. Most of them have some medical relevance. So if we could hold the questions to the end, I'll absolutely get to you. Okay, so next we'll look at units. So same kind of statistics, except this time we have a lot of missing data, right? We have around 6,000 of the records that are missing for the units. Like I said, when you have lab data, it's the lab, test, the value, and the unit. The unit's always where it kills you. So we have a lot of grams per deciliter. And what was kind of interesting is when I looked at the semantic correctness, I said, why is percentage associated with grams per deciliter? Well, if anyone's ever looked at blood alcohol level is described to people as a percentage. What's your percentage blood alcohol level? Whereas medically, what that translates into is how many grams per deciliter of alcohol do you have in your blood? Same thing here with ratio, grams per deciliter. So if you want to understand what are all of these things, how are all these things connected, it bubbles it right to the top based on usage. Okay. So I'll end and then we'll have some questions for the implications for team structure. These are my opinions on how Horton works. You can tell when a speaker says that, he's about to say something you don't like, possibly. And he doesn't want to get in trouble for. So no one record this part. So No, I'm kidding. It's not actually that controversial. So to be successful, in my opinion, based on seeing a lot of data science teams work at this point, your data science team have to be integrally involved in the data transformation layer and the understanding. You cannot throw that over a fence to a bunch of Java engineers and have them do it and then just take the output of it. If you don't grok your data from soup to nuts, you have no way of trusting your conclusions. Your data science teams have to be willing to get their hands dirty. And that's a tough sell sometimes. Because a lot of times I go to data science teams and I see people who want to sit in a corner and write R and don't want to do any of that whole data munging business. They don't want to know about how the sausage was made. But you kind of have to know about how the sausage was made because you have to know when they're putting the gristle in. And finally, all right, actually not finally, but your data science teams have to be allowed to get their hands dirty. Don't protect them so much, managers. They're capable if they know that they're expected to do it. And if they truly believe that this is a requirement, they will absolutely do it because there's no better feeling in this world than for a data scientist to draw a correct conclusion that means something and matters something. It matters about something. Maybe that's biased because I'm in medical and it's really great to have those kinds of insights, but still. And the conclusion, all of these things have come to the conclusion. Your data science team has to have software engineering chops. It seems a lot of the time we have looked at data science, but the original definition was this sort of triumvirate of domain-specific knowledge, statistics and machine learning, and computer science, but we've kind of ignored the computer science and said, well, we can help these guys by offloading this work to people who are not data scientists. By doing that, you're robbing them of insights and you're robbing them of relevant context, so they're giving you bad conclusions. Okay, so I had some questions. I'll take them now, please. You got 5 minutes. Yes?
So an interesting correlation between albumin and bilirubin.
Okay.
So albumin is a protein synthesized by your liver.
Yep.
And bilirubin is actually the byproduct of the red cells metabolism, right? So
Yep.
So the only connection between them is that they're both actually coming from your liver.
Right.
There is no connection between them.
In a medical sense. No, hold on. Let's be clear about this. What this finds is not a medical connection. What this finds is they're used in the same tests. This is a lab. These are lab tests. When you get a lab panel, you will generally be given.
That's your general blood count. Right?
Yes.
That's it.
Yes.
Thank you.
Yeah.
Just a simple question. What is the tech stack that you use, like website, or is this?
Yeah. So this was written in. Sure, yeah. So the question is, what's the tech stack that was used? First off, it's all open source, so you're welcome to have it. Use it if you like. The tech stack was entirely in Spark. All right, so it's entirely done in Spark. It's Spark and Java. So, yes, question. More details about how to find the possible value synonyms. Well, it's very easy, all right? So we're actually using Word2Vec as a vectorization model. So Word2Vec gives you, so the input to Word2Vec is generally sentences, right, in the textual case. In this situation, we're abusing that a bit, and we're saying each element in the row, each column in the row, in a particular row, translates into a word, all right? There's some data munging where you look at the canonical representation as you're binning it based on the percentile if it's a number, right? But that gets fed into a Word2Vec model, and then it looks for synonyms, the strongest synonyms based on cosine similarity in that vector space. And the ones that are strongly connected bubble to the top. And those are strong connections based on usage. So in this situation, given this data, it's strong interconnections based on how those rows look, right? So it'll find things like quasi-synonymous units, right? Stuff like that. Yeah,
You gave a lot of great anecdotes about when your data is very dirty.
yeah.
What about when your data is very big and it takes hours upon hours to even get a count or a group by count? Do you have
Right.
any like rules of thumb where how you should do that iterative process?
Yeah, so learn to sample appropriately. That's the way to do that. And I've been there, and it sucks. What you do is you pull off stratified samples, right? You start with a uniform sample, then you start pulling stratified samples based on what you think is a problem, or where you think the problems lie. And then you do the same kind of analysis. And it's not easy, I mean, this will give you a report, but just because you get a report doesn't mean you understand anything, right? You have to dig into it. It gives you the places to look next, the questions to ask. Questions, any other questions? Well, you learned a little bit about data munging. You learned a little bit about just a little bit about liver tests. You learned some about curses. So hopefully you had a good time. Come up and talk to me if you like it. If you don't like it, go away.